Hello everybody, my name is Christopher Carl, and I'm going to be doing a demonstration for the SR, the special register, or the status register, on the MSP430. This is a demo, sort of, shall we say, a classroom-style YouTube lesson-free thing, prototyping for Dr. Basim Al-Halabi. We're going to get started with a quick little overview. First, we're going to go over the format for which this sort of experiment is going to be conducted. It's going to be divided into three sections: the skills required, the overview, and that's it. Basically, in the skills required, that will be other videos that can be linked directly to. Generally, those will be practice problems or concepts followed by practice problems. And in the overview will be the actual lessons, so the applications, and the lesson and actually demonstrating the use of the microcontroller will be included in those sections. So let's get started. Alright, the first thing that we're going to cover is the status register. It is the overflow negative Z or 0 and carry flags. So some of the skills required is basically conversions and arithmetic with all of the binary forms. So we need to start off with unsigned binary manipulation, moving on to signed magnitude, 1's complement, and 2's complement. For 1's complement and signed magnitude, those are irrelevant in terms of the arithmetic, but it's good to know. The main point is to realize why we don't use them and why the MSP430 isn't using them. Followed up, we are going to review some exclusive OR logic, which will tie into the overflow. We're going to need some CCS foundations, so just basic navigation around both the debugger and CCS as a whole, and some assembly foundations in terms of functions. And those can be, of course, found in other videos if this experiment were to continue. Moving on, let's actually overview why we're going to be demonstrating this. So the reason why the special status register is important is because every single arithmetic operation will affect the status register. So that includes incrementing registers, that it'll include bitwise functions, that includes basic arithmetics, and other things. So it's very important to understand not only what it's doing, but also how to use it. Back in the day, Intel, when they came out with the 8-bit processor, people were excited because that was just enough instruction set they needed to emulate further multiples of 2. So they ended up emulating the 16-bit instruction set and emulating the 32-bit instruction set. But by then, the 32-bit instruction set had already come out on actual chips. But the point is that by using the status register and looking at the bits, one can actually emulate higher orders of instruction, which is important for a theoretical standpoint, simply as a proof of concept that it can be done. Furthermore, this general knowledge of the status register will continue on into further registers down the road. If we can understand the status register and its volatility and also its usability, then we can move on to bigger and better things. Alright, first thing we're going to do is review some XOR logic. This is exclusive OR. Starting off, XOR stands for exclusive OR. Its truth table is as follows. Zero, zero, 0, 1, 1, 0, and then 1, 1. If this is the A and B bit, and this is the Z or output bit, this would be a 0, that would be a 1, that would be a 1, and that would be a 0. Exclusive OR means one, the other, not both. Now this is important because the status register uses this to evaluate the overflow flag. Now, if we were to do an XOR arithmetic or XOR arithmetic across a larger function, let's say 01011 and 001011, this truth table can help us. This is a 0, this is a 0, that's a 1, that's a 1, that's a 1, and that's a 0. Both, that's a 0. One and the other, that's a 1. One and the other, that's a 1. One and the other, that's a 1. Both, 0, both, 0. That covers exclusive OR logic. All right, moving on, we're going to start with conversions from unsigned to 2's complement. So basic binary is a string like this. Let's say a positive integer, which is 0, 1, 1, 1, and also a negative potential integer like 1, 0, 1, 1. So whenever we have a starting bit that's represented in 2's complement, then that means that's a negative number. If this is an unsigned number and we're going to 2's complement, that means that we need to keep this as is. And for this, we need to add zeros in front of it to preserve the sign. Now, let's say this number was given in 2's complement. Let's say we had the 2's complement 1, 0, 1, 1 and 1, 1, 0, 0, and we were trying to convert this into decimal. So to do that, we'd have to convert it to binary and then to decimal. Or rather, I should say unsigned to decimal. So we begin with step number 1, which is getting rid of a 1. So we take off a 1 from here. This 0 becomes a 2. This becomes a 1. Or yes, this becomes a 1. And this becomes a 0. So the carrying can end. Now we have a 1, we have a 1, we have a 0, we have a 1, a 1, 1, 0, 1. To check ourselves, let's go ahead and add back the 1. We have 1, 0, 1, 1, 1, 0, 1, 1, adding the 1. See if we get that previous number from before. 0, carry, 0, carry, 1, 1, 1, 1, 0, 1. Looks the same to me. Okay, now we're in step 2, which is the inversion. So you go 1, 0, 1, 1, 1, 1, 0, 0, and inverting becomes 0, 1, 0, 0, 0, 0, 1, 1. And now we are in unsigned form. So we can go ahead and add it all up. Let's see, this is an 8th place, 16th place, 32nd, 64, so we have a 64, plus a 2, plus a 1. We have 67. And if we go into our calculator, and choose our programmer mode, and select binary, and put in 1011, 1100. Oh, whoops. That was the 1's complement. We need 0, 1, 0, 0, 0, 0, 1, 1. We got 67. That's our decimal number right there. Wonderful. All right, moving on, we're going to go into unsigned addition. And I'm also going to quickly overview subtraction while we're at it. So let's start with the basics. Let's go with 1, 0, 0, 0, and let's add a 1 to it. Well, in base 10, we have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In base 2, which is binary, we have 0 and 1. That's it. So when we have a number like 9 and 3, we don't have anything called 10. We have something called 0 and a 1 in the 10th place. That same concept applies here. When we have, let's say, a 1 and a 1, we don't suddenly get 2. When we add a 1 and a 1, we get a 0 in the 1's place and a 1 in the 2 to the 1st place. So, going by that, we have 1, 0, 0, 1. Another example. 1, 1, 1, 0, and 0, 0, 1, 1. We have a 1 here. These two create a carry, but total is 0. These two also create a carry, but total is 0. These two also create a carry, but total is 0. Wonderful. And finally, whoops. Finally, something very ghastly. How about? And then 1, 1, 1, 1, 0, 1. That's a 0, but with a carry. That's also a 0, but with a carry. That's a 1, because these together equal 0. That equals a 1, but it still has a carry. We can never go more than 20, for example. We can't go more than twice. So we get a 0 down here, but that's still a carry. That's a 1 down here, but that's still a carry. This is a 0 down here with a carry. That is a 1 down here with a carry. And that is a 0 down here with a carry. And we get that. Very nice, ghastly number. And if you'd like to check your work, just to make sure that it was correct, you can go back to the trusty calculator again. Select binary and say 1101, 1111 plus 111101. And we get shit. Let's see. 1101, 1111 plus 111101. Yeah, the numbers don't lie. I fucked up. Alright, let's go back. Let's go with a ghastly one. 1101, 1111. Let's say 111, 1010. 1 plus 1 equals 0 with a carry. 1 plus 1 equals 0 with a carry. 3 ones together equal a 1 with a carry here. We have a 0 with a carry here. That's a 1 with a carry here. It's a 0 with a carry here. That's a 1 with a carry here. That's a 1 and 0 with a carry here. Now if we go to our trusty calculator and see what we got. Start with 1101. 1111 plus 1110101. And we have the right answer. Wonderful. All right, moving on, we're going to go ahead and deal with 2's complement addition. So we'll start out with 4. A nice example. Let's stick with positive for now. Let's go with 01111 and 0101. Change that to, let's say, a 0 and a 11. Make our lives easy. We got a 0 and 1, a 1, 1, a 1, and nothing's ever easy, is it? Okay, so we start off with 2 positive numbers, so we got to keep it that way. So even though we ended up with 4 here, it's with the understanding that there are lots of zeros previously. Same thing goes with negative numbers. So let's start with 1101. Seem to like that one for some reason. And 11. Can't do the same again. That'd be nuts. 11. That's a 0 with a carry. That's a 1 with a carry. And that's a 1. So we have the understanding that even though we ended up with 5, over here to the left, more 1s continue out into infinity. And the same way goes with the zeros over here. So now let's add 2 numbers together that are obviously very different. Let's go with a nice example. 1101, heck, why not? And a nice positive number, 1111. Now let's see. Unfortunately, I'm not so fantastic with 2's complement, but we can do this real quickly to figure out what this is in decimal. So to do that, we do step 1, which is subtracting. And then we do the inverting. So this is the number 3. And this is the number 5. So 3 plus 5 should give us a positive number, right? Nope, that's a negative 3 plus 5. So this should give us a negative number. And let's see what happens. That is a 0 with a carry. That's a 0 with a carry. That's a 1 with a carry. It's a 0 with a carry. That's a 1. Oh, look at that. With the understanding that there are 1s off to the left of it as well. Wonderful. Okay, so let's go ahead and do some basic CCS manipulation. Okay, if we open up CCS, Code Composer Studio, and plug in our microcontroller at the same time, and wait for that little thing to come pop up. Here we are. All right, I've loaded a nice little program that will go over for us how to use Code Composer Studio. So currently, just in case, I'm going to go ahead and go to Properties here and make sure that the family is the MSP430, and in this case, my variant is the G2553. Wonderful. Same, make a nice bug there, a nice bug there, and another bug right here. And I try to debug this. Errors exist, okay, cancel. But nothing shows. Nothing shows like where the errors are, except for a few of these things here. And it says undefined symbol. Haha, very helpful. Okay, so let's go back. We're currently in CCS debug mode. Let's go to CCS edit mode. And instead of hitting debug up here, let's hit build. Okay, you saw something that just flashed. A lot of errors are here, and sometimes you can go ahead and pop right to them. But every once in a while, like this thing, I can't even click it. So I go to the console. It says error at line 49. Okay, that's useful information. Okay, I can get rid of that error. There's a line at line 60. No, at line 75. Okay, I can get rid of that error. There's a line at 255, which is another way of saying FF, by the way, in case you're trying to get better at that conversion stuff. All right, undefined symbol overflow app 1. Okay, so I never actually used it, so I used overflow app 2. There's one at 279 that says overflow app 2 has already been defined. Okay. Aha, so I'm using overflow app 2 up here, but if I use that up here, it's going to be trying to jump to that, but it's already been defined. Let's try building this again. Okay, looks a lot cleaner. Let's go ahead and do the debug. Now, in case you don't see any of these windows, let's say all what you've got right now is this. What you can do is go to View. There are a few things that you want to grab out. First of all is the console. Might as well view problems. We've all got problems. Now, if you don't like the layout, you can always drag across the many different areas of the screen. But I also want you to bring out the memory browser. And I also want you to bring out the registers. And if you could, lay it out this way so that you can see most of your code and see the registers at the same time. All right, let's go ahead and hit debug. Yeah, because we hit debug already. Okay, here we are. At the memory browser, I would like you to enter if it would load the symbols. Okay, great. Enter in location number OX200. You can hit right click, fill memory, with starting address 0200, length just below 200. It is 1 below 200. This is the size of the G2553's memory, and the data value is 0 at 8 bits. And there, clean as a whistle. So I also want you to go inside of registers and hit core registers. Again, this is just an overview. Let's go ahead and expand SR for now. You won't be seeing this, you'll be seeing defaults for all of your values. Now, default is just another way of saying hex, because hex is the most useful way to have a look once you've gotten used to hex versus binary and that sort of thing. But I will actually show you, for the purposes of this demonstration, why redisplaying stuff, sometimes in signed integers, sometimes in unsigned integers, may be more beneficial to you than others. So let's go ahead and start. Up here, I can say step over or step into. I'm going to start off with F6, which is step over. Now I'll start with F5. Now I'll start with F6. Okay, that does the same thing, except when you come across subroutines. I'm going to press F6 so I can go through that subroutine. And that is a custom function I built that clears RAM. And then, let me say I step into this subroutine. This is going to clear out all of my registers. As you notice, some of them had data from either the random start or from previous entries. Now we return. Now, for the first addition, we go with the value 3. We're going to move that into R4. We see that over here. And then move R5, move 5 into R5. Move R4 into R6. So just copying that over there. And then adding R5 into R6 and storing it in R6. So we get the value 8. Totally makes sense. And just so that we can remember what we did, this will move R6, whatever is in R6, into the address stored in the register R15. In this case, it's OX200. That same memory area that I designated previously. I'm going to go ahead and change the font so that it's slightly bigger. I just realized. Should be in appearance, colors and fonts. Edit the font to size 20. So now everything's giant. Great. Except for those pea shooters. Okay, also, normally it would say 16-bit style hex, but I'm going to go ahead and change it to 8-bit signed integer for the demonstration here. All right, we're currently on this at line 42, moving onward. So now I'm actually going to change these from the default hex into binary. So you can see exactly the same thing that we were doing before by hand, this time done by the microcontroller. And if you can't select it, just select out and then select back again. It's finicky like that. Okay. So what we should expect is R6 will be cleared, and that happened. -3, which is preceded by a bunch of 1s, and then here's that 3 portion, which is inverted 3 and -1. And then -5 should be put in R5, and it is, preceded by a bunch of 1s to designate that it's a negative number. Copy this into here. Add this into here exactly as before. And we get a bunch of zeros this time. Wonderful. And now we go ahead and store it. We get -8, exactly as promised. 3 minus 5 should be -2. And it is. -3 plus 5 should be +2. And it is. 56, which is a larger number, added with 60 should be a larger number like 116. And it is. -56 with -60 should be -116. And it is. 56 minus 60 should be some number -4. Yeah, that makes sense. -56 and 60 should be 4. And it is. And that completes our review of CCS. Now we're actually going to go back into OneNote and learn about the status register, which is this thing right here. So the status register is composed of several bits. It's actually a 9-bit for the purpose of this microcontroller. It's a 9-bit register. It contains all 16 bits, as you can see here. It's got all 16 in there, but it goes up to 9, and that's what the V is. This corresponds 1 to 1. So C is the 0th, Z is the first, N is the second. GIE, which is the interrupt, is the, in this case, the third. CPU off is the 4th, 5th, 6th, 7th, and 8th. But this means the 9th. So if we started from 0, then this would be the 9th. If we're starting from 1, then this would be the 9th. If we're starting from 0, then this would be the 8th. Now, this is called the interrupt flag, this is called the negative flag, this is called the 0 flag, and this is called the carry flag, and you can abbreviate them as the letters have shown. I'm going to go ahead and stop this, take out my microcontroller, and then head back into OneNote. Alright, so the first thing when talking about the status register is the discussion about the carry bit. So in the status register we have the overflow flag, the negative flag, the 0 flag, and the carry flag. We're going to start off with this buddy. So in normal base 10 arithmetic, let's say we have the addition 15 plus 16. Let's make that an 18 just to differentiate. When we add 5 plus 8, and we count on our toes, that is 13. The problem is we can't represent 13 in one space. We need to represent only one digit, so we choose the 3, whereas the 1 goes up here and it so-called carries. Hi, how are you, gorgeous? That was my cat. And the carry is added across the entire row, so this will be 33. Now, the same thing works in binary. So let's say we have a addition like this. And we have 1 plus 1 that equals 0. The carry carries over here. Because in normal, it looks like this. Except we can't register these two in this one place. So we have the carry over here. Then we add these all together, and this carries over as well. This is all good and nice for arithmetic in, shall we say, normal operation, but if we have something like restricted arithmetic, for example, 8-bit, or in our case with the MSP, 16-bit arithmetic, then the subject of a carry bit makes a lot more sense. Let's say we have the total arithmetic of 1101, 1000, 1000, 1111. Go ahead and do that out. 111, that's a 0 with a carry over here. That's a 0 with a carry over here. That's a 1 that falls through. That's a 1. This is a 0. Okay, this is where it gets tricky. So normally we would carry the 1 over here, and there's this blank space, if you will. That space is kept blank because the in the case of an 8-bit microcontroller, they don't have any more space here. What they do have is what's called the carry bit, and that's where we place it. So in the case of 8-bit arithmetic, we keep the addition 8 bits no matter how big the true number is. And the carry just represents whatever is left over in that sense. So let's go ahead and do some more examples. Alright, our first example is going to be, select a pen. This will be 0 OX01 plus OX01. And the answer to this is OX02. Now if we do out the binary, I'm going to draw it in a particular way. I'm going to say 0000, 0001, and repeat the same on the bottom. This becomes a 2, that becomes a 0 with a carry. That's a 1, 0, 0, 0, 0, 0, 0, and there's nothing over here. There's no carry here. So in that case, this so-called carry bit is actually 0 because nothing was carried through. That covers that example. The point is that even though there was a carry even here, it doesn't translate all the way down to this box over here. So in our next example, we'll have a contrary OXFF and OX7F. Alright. And the answer to this is 7E. Let's go ahead and do this out. So we start off with 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, and 1, 1, 1, 1. Do this out, we get 0, 1, 1, 1, 0. Sorry, it's 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and that's a 0, and we should carry over a 1, so we'll let that fall into the carry bit. So even though we had a lot of carries over here, it is this final one at the very most significant bit on the left-hand side which matters to us. Doing another example. Now we have OX01 plus OXFF. And the answer to this is going to be 0. So, to prove that, let's go ahead and do the addition. 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. And there's a carry bit right here, just to represent that. So let's go ahead and do this out. Even though it would be technically easier to do it the other way, just for visual, we'll go ahead and do it as it is written. So that's a 0 with a 1 carry. That's a 0 with a 1 carry. 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 Again. So that carry follows through. And that covers the carry bit. Now, the way that we should interpret this is that if we had 9-bit arithmetic, or even 16-bit arithmetic, using the same example, this would be OX 0001 for 16-bit, OX 00FF for 16-bit. The answer would be OX 0100. And to prove that, let's go ahead and draw this out. So this will be 16-bit. See, get my pen again. This will be the carry. Start off with 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 1. And now we go ahead and do 1 1 1 1 1 1 1 1 0 0 0 0 0 0 0 0. All right, let's do this. That's a 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 1, and then 0 0 0 0 0 0 0 0. So that's the point. Now that we can visually see why 8-bit arithmetic results in a 0, whereas 16-bit arithmetic results in an 0100. And that's the same kind of restriction that we find all over the place because of that 8-bit arithmetic. Now, for the purposes of demonstrating in the microcontroller, I'm going to show you that 8-bit arithmetic, but know that even though it's a 16-bit arithmetic unit, you can still do that full sort of addition in 16 bits, and you'll still experience the same effect. Okay, the next thing we're going to cover is the 0-bit. Let's go ahead and do some drawing here. So the 0-bit, this is the way of saying it. The 0-bit or 0 flag goes high, or 1, if the answer is 0, no matter if an overflow or if a carry is present. Okay, so let's go ahead and do some more examples. First example is going to be 0x04 plus 0xFC. Let's do this out. This time we have not only the carry bit, but we also have the 0-bit. So it was 0 0 0 0 0 1 0 0 0 0 0 0 C. That's 10 10A 11B 12C. Okay, so that's a 12, so that's a 1 1 0 0. Oops, and the F is definitely not zeros. F is 15. So 1 1 1 1. Wonderful. Okay, that's 0 0 0 with a carry, 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 0 with a carry. Okay, so the carry drops through. This thing is equivalent to 0. So the 0 flag goes high. All right, let's do another example. OneNote is surprisingly tricky. All right, our next example is going to be OX01, OXFF. And surprise, surprise, we're going to get 0 to demonstrate this. Let's go ahead and do this out with our carry bit, which is currently 0, and our 0-bit, which is currently 0. 0 has not yet been detected in the answer over here. So that's 0 0 0 0 0 1. 1's all around. Do this out, we get 0 with a 1 a carry, 0 with a 1 carry, 0 here with a 1 carry here, 0 here with a 1 carry here, so forth and so on, until we get a 1 over here, and we have to add that into our carry. And the detected answer is 0, so the 0 flag goes high. That's it. And now for the final example, we're not going to do arithmetic, we're actually going to do logical applications. So OX CDA3331C. This is a particularly favorite of mine. And C3. We're going to logically AND these together. So let's draw this out again with our carry bit currently at 0 and our 0 bit currently at 0. No 0 has been detected yet. So a 3 is represented as a 1, 1. A C, which is 12, is represented as a mirrored 1, 1. So you can see that I purposefully did this to be inverses of each other, so that when we AND them together, 0 and 1 is a 0, 0 and 1 is 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 0, 0, 1 is 0, 0 and 1 is 0, 0 and 1 is 0. And we don't have anything to carry in the AND operation, so that stays 0. But the 0 flag has been detected because we have a 0 in the answer down here, so that goes high. Alright, that covers the 0 flag. And zeros, I should say that zeros go high in a few cases. They go high if two numbers are compared. Well, I should say the 0 flag goes high in compare operations. It goes high sometimes in decrement operations, sometimes subtraction operations, addition operations, sometimes increment operations. And these are situations where you would use some kind of jump, like jump 0, jump not 0, and other things like that. So now we'll contrast that with the negative bit. Alright, for the negative bit, this is a particular bit that relates to the answer in the same way that the 0 bit did, but in a slightly different way. So when we do normal arithmetic, like, 1, 1, 1, 1 plus 0, 0, 0, 1, and we get 0 with a carry here, let's say 0 with a carry here, 0 with a carry here, 0 with a carry here, and a 1 with a carry here, so we get this. This is understood to be a positive number because there are zeros trailing all the way over it in 2's complement. But if we were to do this in 4-bit, where we are restricted, and the answer that we get is restricted to that size, and we get 0, 0, 0, 0, then that becomes a strictly 0 with zeros followed by it. But let's say we were to change this up, and we get 0, 1, 1, 1 plus 0, 0, 0, 1, and we get this 0, 1, 0, 1, 0, 1, 1. And we restrict it to this 4-bit math. In 2's complement unrestricted, that's understood to be a positive number, but if we do that here in 4-bit math and restrict it just to 4 bits, then we get 1, 0, 0, 0, and the microcontroller believes it to be a negative number because it assumes that there are 1's trailing in front of it. The reason for this is because the leftmost, or what we call the most significant bit, dictates the sign. And whatever it is, the sign, it is theoretically assumed that that same number that's inside of that signed bit trails at the left edge, indefinitely onto infinity. And this becomes useful for a few sort of functions. Let's go ahead and do a couple. All right, for the first example, we've got 0x, 0, 0, and then plus 0x, ff, I believe. And the answer is just going to be 0x, ff. So let's do this out again, except this time we have the carry bit, the 0 bit, and the negative bit. That's a 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. So the math is real easy. It's just ones all around. Now, we didn't have anything to carry, so that's going to be 0. 0 was not detected, so the 0 flag does not go high. But it is a negative number. So we flag it. Turns out that the most significant bit is always the negative bit, so to speak, and mirrors it. So in future representations, I'm going to draw just this stuff. Let's do another example. Let's add the highest possible, or I should say the lowest possible negative number with the lowest possible negative number. That becomes FE. So this is like adding -1 and -1. Let's see how that looks like on paper. Draw out all those ones. And we have a carry bit, a 0 bit. Both of these are currently 0. And the negative bit, which is currently 0. Okay, let's go ahead and add these together. We get 0, 1, that's a 1, 1, that's a 1. This is going to happen quite a bit. And now this goes high, and there's a carry, so we change that. The 0 flag should not be changed, and that's our answer. So that negative bit did go high, same way as it would normally. All right, so that covers all those bits. Wonderful. Now onto one a little bit different. Oh, I should also mention what functions this one changes. The negative bit can go high and compare. It can go in add, subtract, decrement, definitely, increment also sometimes. And this is helpful for checking the n bit in the jump less case, and also in the jump greater JGE case. Jump 0 and jump 0 and jump not 0 are not applicable here, because if there is a negative number, then it can't be 0. If there is a if the negative flag is high, then the 0 flag is not going to be 0. So I guess you could say sometimes jump not 0, sometimes, but really the ones that you need to worry about are jump greater than equal and jump less. Alright, now we've come to the meat and potatoes. This is the overflow bit. The overflow bit is arguably simultaneously the most important bit and the least important bit. Mostly because if you were trying to use emulation, or you're trying to double check your arithmetic to see if you went over the arithmetic possible, that would mean either one of two things. A, you're using a very small microcontroller, in this case a 16-bit or 8-bit, when today we have 32 bits, and that can represent nearly any number that most people can think of. And then today we even have 64-bit processors. So that means that there is literally an unthinkable number of numbers that microcontrollers and microprocessors these days can come up with. But there might still be a reason why you would look at the overflow bit, and that is for your sanity. Because when you're learning this stuff, and you're doing these additions, and you're coming up with the answers that are completely impossible, it would do you some good to have a look at the overflow bit. Now, there's a reason why I had us review exclusive OR logic all the way back up here. And there's a reason why I introduced the carry bit first, and the 0 bit and the negative bit afterward. Because the overflow bit can be computed in one of two ways. I call this the easy way and the hard way. And some other way. Ultimately, you can design any number of circuits. To feed into itself, or into others, or into others, and to come up with some possible thing at the very end out of two inputs. The overflow bit is some kind of circuit that is implemented per microcontroller manufacturer. And the way they do it is either one of two ways, generally speaking, or some novel way that they came up with on their own. One way is to keep track of what is the most significant bit for both numbers. And the other way is to keep track of the carry in on the most significant bit and the carry out on the most significant bit. For simply the answer. This one requires all three to be considered. Let's go ahead and consider the easy way first. So this is considering the most significant bit of A and B and Z. So let's go ahead and do an example. There are two rules that are guiding principles. Adding two positives should be positive, right? I mean, if I add a positive 10 and a positive 10, I should get a positive 20, right? Not if I add a positive 10 and a positive 10, then I should get a negative 20, right? That can happen. That can totally happen depending on the size of the microcontroller. If the microcontroller is so small that it can't actually represent negative 20, for example, in a 4-bit, the highest it could possibly go is representing the number 15. So how could it possibly represent something like a negative 20 when the most it could possibly represent is probably negative 16? This is what we would call an overflow, because the arithmetic goes over the total capacity and power of the instruction set. So the second rule on top of that is the same way. Adding two negatives should be negative, right? Because negative 10 minus 10 should probably equal negative 20, not negative 10 minus 10 equal positive 20. Which could totally happen in a 4-bit microcontroller. We're dealing with, in this case, a 16-bit microcontroller, but we will demonstrate 8-bit because it's easier on the eyes. So let's go ahead and start off with an example like OX7F plus OX07. Now let's go ahead and do our fancy little square. That's an O1111, 1111. And that's an O000 and an O111. Let's just go ahead and do this. So here's our negative. That's our 0. I'm sorry, that's our carry. That's our 0. And now here is the vexing overflow. Adding together, we had 0, 1, 1, 1, 1, 1, 0. The ones fall through. Sorry. That was a 0 with a carry. Another 0 with a carry. Another 0 with a carry. And there it is. Okay. So nothing carried through. It's not 0. It is negative because the 1 is over here. So what about the overflow? Well, I'm going to ask you to get rid of these for a moment and look for a quick moment. This is a positive, right? This is a positive, right? We added them together. So why is this negative? It's because adding these two numbers together made this bit overflow. If this bit had any other choice, or rather if we had another 1 bit over here to make this a 9-bit arithmetic, then we could totally have a 0 over here and a 1 over here, and the rest of the string would follow and it'd be correct as a positive number. But because we are constrained to only 8 bits of size, we have to use that limitation. So, adding two positives should be positive, adding two negatives should be negative. This is a simple case of case 1. So we compare 0 and 0. 0 and a 0 should not equal 1. So that means we had an overflow. Incidentally, the hexadecimal of this is 86. Moving on to another example. We have 7F, 7F again, and we're adding them together. Let's see what we get. That is an O111, 1111, same thing. Here is our negative bit. Here is our carry bit. Here is our Z bit. And here is our VED bit. Wonderful. 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0. Oh, what the hell? Why did this happen? Another positive, and we got a negative. That means we have an overflow. Now, let's do a final example using this so-called easy method. Oh, no, that was it. Okay, now let's do the hard method. The hard method is most likely what the microcontroller is actually using. And yes, it may be hard to wrap your head around it, but once the design has been placed, it's a solved problem. So, whereas the previous had a look at the most significant bit of the first, the second, and the answer, the hard method doesn't really do any of that. This second method has a look at the carry in, carry out of the most significant bit of the answer. So let's go ahead and have a look. This will be a case of 2. 2 negs should neg. So we're going to get an overflow, that's for sure. And in this case, we'll see an example of a negative, 2 negatives going positive and overflowing that way. All right, here's our example. OX8F, so you'll notice that there's a 1 in the leftmost side. That means it's negative. And in 9F, same way, which means it's definitely negative. All right, so I'm going to draw this in a particular way. Hope you don't mind if I do. This is a 1, 0, 0, 0. It's a 1, 1, 1, 1. That is a 1, 1, 0, oh, definitely not. 1, 0, 0, 1, and 1, 1, 1, 1. Now, I'm going to draw the carry in over here. Of the most significant bit. and the carry out over here. And now everything is as normal. 0, 1, 1, 1, 1, 1, 1, 1, 0 with a 1, 1, 0. This didn't carry anything. 1 and 1 is a 0, but this carried something. So it's not 0. So then how do we compute the overload mathematically speaking? Going up here, it's the Cn, MSB, Cin, XOR, MSB, C out. Phrased again, that would be this thing here, XOR this thing here. So in this case, we have a 0. I believe that's an exclusive OR. 1, which equals a 1. So the overflow flag goes high. And the same you can check yourself with 2 negatives should be negative. But in this case, we had 2 negatives and they gave us a positive. All right, the crowd wants another example. So just for good measure, we'll make it extra nice and neat. This will be OX80 OX95. Haha, just kidding. 9F. And we draw our nice little thing there again. That is a 1 0 0 0. 0 0 0 0. 1 0 0 1. 1 1 1 1. That's our negative bit. That's our carry out bit. That is our Z bit. That's our VED bit. And some kind of carry in. So let's do the arithmetic. 1 1 1 1 1 0 0. This has nothing carried in from these two previously. 1 plus 1 is 0. We get a C out over here, which is a 1. And it's not 0, that's for sure. 0 exclusive OR 1 equals 1. The flag goes high indeed. And that concludes the overflow bit. Long-winded chapter indeed. All right, so now let's go back and have a look at what we need to do next. The status register. We have to talk about the status register. So we practiced everything, and we just need a demonstration of how this all comes together at the very end. So let's go ahead and move into the final phase of this lesson, which is the practical demonstration of everything that we've discussed up until this point. Using the exact same hand-cranked stuff that we were talking about, it'll be demonstrated that the status register not only is needed, but it tells the whole story when we're constrained by a single-sized set arithmetic operation opportunity. So let's go ahead and compile and debug. Open up our memory browser. Go ahead and open those core registers and expand that oh so important status register. All right, let's do this. So we're going to step into, now we're going to step over this method, which clears the RAM, and then step over this method, which clears the registers. 3 plus 5 is 8, and that'll be shown. -3 minus 5 is -8. All right, you guys have seen all this before, right? Here, we'll go ahead and add a breakpoint. And we can hit either play or resume, which is F8. I guess there was another breakpoint there. Hit 8. And look, all of those arithmetic operations have been computed for us. Now, let's go ahead and see and have a look at what regular addition looks like according to the status register. While it is important, these upper two lines will pay more attention to the status register than any of these others. So moving on, we move 3C into R4, and move 23 into R5, put them both into R6 and see what happens, and then store it. Okay, so we got the value 95, great. Nothing happened to the status register whatsoever. Okay, so this is the carry bit section. Let's have a look at 1 plus 1 equals 2. Now, before we do the computation, we had already proven before in the carry bit section that 1 plus 1, while has a carry internally, doesn't have a carry all the way to the end. And that should be reflected up here. That 0 should stay the same. And it does. Moving onward. Let's move -1 into R4 and some other negative, nope, that's a positive number, into R5. As you can see, there's a 0 right here, and there's a 1 right here. So this one's negative, this one is 0. So that's positive, because we're using bit size or byte size logic as opposed to word size logic. Add them together, and what did we predict? We predicted that there would be a carry. So let's see if the carry bit goes high. And it does. And the total value is 126, just if anyone's curious. Now we add 1 to -1. And let's see if the carry bit went high when we tried it. Or did we try it? Oh yeah, we tried it. Okay, yep, there's a 1 there. Let's see what happens. What do you look? There's the carry. And you'll also notice that because R6 is 0, the 0 flag did go high. That's a byproduct. So now moving on, let's go ahead and go into the next section where we demonstrated the 0 bits. All right, let's move the number 4 and a small negative number, you guessed it, -4, into R5. Now let's have a look at the 0-bit demonstration. Even though it's kind of obvious, might as well. There it is. But it does have a carry, but it is still equal to 0. Even though this carry thing is indicative that there's some larger number that was supposed to be the case, that 8-bit logic that we're going with is going to cut that short and make it a 0 instead. It's not an overflow. Overflow doesn't mean that it should have been a big number. It's a carry. Moving on to the next example. We have 1 plus -1. Oh, again, whoops, that's rough. And now we have that sweet little mirrored one. So we have 3C and then C3. As you can see, those things are together. Now, normally I have an add function at this section, but I changed it to AND. So let's see what happens. And yeah, the 0 goes high. And you'll notice nothing happens else, like nothing was carried per se, or we don't know that for sure, but gut instinct was going to tell me no. Moving on to the negative bit demonstration. We start off with putting 0 into the first one, and put -1 into the second one. And in the same way that we computed up here, that there's a 1 all the way in the leftmost position. In this case, the most left position is the 8th section, or the 7th slot rather than the 15th. And the negative bit did in fact go high. Look at that. So now we are adding -1 and -1 together. Let's see what happens. We get -2. And as we found out, it has a carry and the negative bit is high, just as we had predicted. Finally, the overflow bits. So we start off with the largest possible integer we could possibly come up with that's still positive. And we add to it 7. Now, normally we should just get, a larger number. But according to our previous calculations, the negative bit should go high, and so should the overflow flag. And that is the case. Because these are both definitely positive numbers, but we still got a negative number. And the reason for that is because we had that overflow. Moving on, without breaking my code. All right, we moved 7F and 7F. So this is just adding very large numbers together. I'll tell you what, it kind of buggered out, so I'm going to go ahead and hit restart. And jump back to where we left off. Okay, here we are again. So we go ahead and put All right, so I'm going to go ahead and remove all the rest of these breakpoints. I'm going to stop the debug session and have everything play all the way back to where we last stopped, because editing all of these lines while debugging causes it to graphically seem to not be in the right place. And we have errors. All right, let's go into the build. Have a look at the console. There's an error at line 197. What could this be? Oh, that is a huge syntax error. Yeah, in assembly, syntax errors matter. Okay, I'm going to open up those core registers, open up the memory location, scroll down to where we were last. Play it to where we were last. Okay, here we are. Moving on. This is a very large number mixed up with a very large number, both of them of which are positive, and we will find, according to our previous prediction, that not only does it go negative, but that's a mistake. The overflow indicates that that negative should not be negative, and it's a mistake. So that overflow is telling us the whole story as it is. You could even say it's a false negative. Haha. So this is a small, this is a very, very large negative number. Let's see what kind of negative number it is. Let's make it a signed integer. It thinks, that's too bad. It thinks that this is a 16-bit microcontroller, therefore that 0 in front of it is still going to make it a positive number, but it's still a 1. Either way, take my word for it, very large negative numbers. Let's move them together. Let us add them first on paper, rather than just taking it for granted. we should get a 0 in the negative, so it should be positive. We should get an overflow, and we should get a carry. And that's what happens. Overflow and carry went high. Now let's move it. See, they were two huge negative numbers, and they went positive. Like, what the heck? So now the largest possible negative number, so this will be negative 127. And then a pretty large negative number. Move those together. And the final exercise that we did. Okay, so it's not negative. It goes positive. There is a carry, and we should have an overflow. And that's what happens. Now, this is extra. Because subtracting also has the same effect. Now, in reality, this microcontroller, according to the documentation, actually does a few arithmetic operations on those registers whenever you use the sub function. In fact, it just adds the inverse. So instead of subtracting -1, it would be adding +1. Or instead of subtracting +17, it would add -17, which to the microcontroller makes no difference. Everything is just an addition problem at the end of the day. So it's still susceptible, as the add is, to the overflow and carry and negative and Z bits. Now, because of that inverted logic, that same kind of logic that we had up here, where adding 2 positives should be positive and adding 2 negatives should be negative, there should be a little asterisk right there. Adding or subtracting, what did I have here? A negative from a positive should be positive, like number 1. And number 4, subtracting a positive from a negative should be negative, like number 2. And we'll find in this example that that's just not the way it is when you restrict our arithmetic. Notice what's occurred. We tried a kind of small positive number and subtracted it from it a somewhat small but medium-sized negative number. So we had a mid-range size positive number and added to it basically another positive number. Well, then no wonder that the result is not positive because it overflowed. Because this positive number, when added with this, in reality is actually a positive number once the subtraction operation has occurred, causes this thing to overflow and make it appear negative. Moving on, the inverse is also true. We have 2 negative numbers, we're trying to have a somewhat mediocre negative number and subtract from it the biggest possible integer possible. This is not going to end well. No wonder it goes negative all of a sudden. Subtracting a positive from a negative should make it go negative. And it went positive instead. So this actually concludes the very first lesson that I'm going through. I have to say it was quite not only fun but enlightening to deal with, and also I'm very excited to see Captain America Civil War, with all the buddies that I took microprocessors with. Please, if you liked it, rate, comment, subscribe. And for those of you evaluating this for actual content, please feel free to leave a comment and critique my work or give any kind of pointers that you would like to suggest. This is Chris Carl. Thank you so much for your attention, and bye-bye.